So if we start with the fact that force is equal to the instantaneous rate of change in momentum with respect to time, then we can play a game with this. I'm not sure if we've done it already or not, where we treat this not as d dt acting on p, but instead as dp divided by dt, in which case we speak of this no longer as the derivative of p with respect to t, but each of these two things, dp and dt, are called differentials, derivative differentials, different things. But if we treat this as a ratio of differentials, then, come on now, then we can take that idea and then multiply through by dt, and we get that dp is equal to the force as a function of time times dt. And this then leads to our taking that the change in p, which is the integral of adding up all the little teeny infinitesimals of change in p from the first to the last p, but I can replace dp by f dt. And the limits of integration now are time limits instead of momentum limits. But this then allows you to sort of move between f is the derivative of p with respect to t, and p is the derivative of f with respect to t. I'm sorry, the integral of f with respect to t. Notice, however, that it's not really p, it's the change in p. And this quantity, the change in momentum, is equal to the force times the time over which the force acts. Last year we dealt with that very crudely, and we had, I guess I have to write here, that impulse was equal to the force times the time over which it acted, and we had the fact that that was equal to the change in momentum. And we did quite a bit with that last year. I hope you recall it fondly. This year we get the increased subtlety that it's not, the force need not be constant as a function of time, in which case you would do this integral of force with respect to time, and that would be equal to the impulse, and the impulse is equal to the change in momentum. The impulse is defined as this integral, but it is equal to the change in momentum, even though it is not defined that way. And at this point I have some pictures which I don't think I have room to show you. Yeah, we'll just put them over top of other stuff. That here is force graphed as a function of time, and of course the integral in a graph of force versus time would be the area under the curve. So there with a J you see the impulse. Last year, of course, we acted as if the force would be constant over the whole interval, and so we had F times delta t was impulse, but really it's the integral of F with respect to time that is the impulse. So here you have a checkpoint. You have a man falling into the snow, and you want to deal with change in momentum and impulse and force based on what you learned in the previous slide, and answer these three questions before going on. Next we're going to deal with collisions, and we start with elastic collisions, and that means a bouncy collision, and that means there's all the motion that goes into the collision is still present after the collision. We have then that because the forces are internal, it's a collision, so it's only internal forces. You do not have external forces. You're going to have momentum being conserved. And because it is a bouncy collision, because it is elastic, you will have kinetic energy being conserved before and after the collision. Because it bounces apart, there are two objects after the collision. We presume that you've been told the mass of the objects and what the initial conditions were, how fast they were going initially. But to solve for these two final velocities, you will need to make use of the fact that you have two but simultaneous equations, and you will work with the two of them. Recall that for inelastic collisions, it's still a collision, so it's internal forces. Momentum would be conserved, but kinetic energy is not. In fact, the definition of an elastic collision ought to be kinetic energy is conserved. In an inelastic collision, a tremendous amount of kinetic energy disappears, and where does it go? It becomes heat. But in an inelastic collision, if it's perfectly inelastic, then you only have one object afterwards. And so you only need the one momentum equation to solve such problems. The book then takes this pair of simultaneous equations and they work them through to solve for the final velocity of one and the final velocity of two, given the initial velocities and the masses. And they come up with some pretty ugly equations, which I would not recommend that you memorize. But they then, or actually previously, they make the simplification of assuming that the target, this object 2, is stationary before the collision. And when object 2 is stationary before the collision, boom, boom, the simultaneous solutions of these equations comes out not too bad looking. And it's very convenient to learn these. You don't have to. It will be a convenience to know those two. I want to use these two equations in the subsequent discussion, but you don't have to memorize these. You could always get there by having a 0 for those V2 initials and then solving them simultaneously. It will get you right to this point. And that might be better than memorizing. But I think you would not be sorry if you memorize those two equations. So let's take those two equations, which I've written here again, assuming we had not memorized them, which are only true under the conditions that the target is stationary, and let's look at a collision between two objects of equal mass. And so these m's are the same for both of them, and the initial velocity, well, whatever it is, this would be m minus m. That's a 0. And so we get that the final velocity is going to be 0. This ball will stop. And the second ball's final velocity, well, that's going to be 2m over 2m, because the m's are the same. Then that's going to be a 1. So the final velocity will go off as the same velocity that the other one came in. And this principle you have seen many places, from croquet balls to this toy called Newton's cradle. We'll look at it again when we're in class. But here is the results, and that ought to be familiar with you, that this ball will come in and stop, and this ball will take off at that same velocity. Much more interesting is to consider the case where the target is very massive, where the target is much more massive than the projectile. Whenever you see they give you a problem and they give you this double greater than, or they say is much more massive, then what you need to do is to get that more massive one in the denominator of a fraction. That what you do is take this equation and divide by m2, because it is the more massive one. So everything gets divided by m2. And then, because m2 is much more massive than n1, the ratio m1, m2 approaches 0. Here too, it approaches 0. And what we have is negative 1 over 1. That the result is that the velocity of the projectile will be the same magnitude but in the opposite direction. That is, this thing's going to smack into this thing and it's going to be like hitting a wall. It's just going to bounce straight back. Now if we consider the target, what's going to happen to it? Well, again, take this equation and divide everything by m2 because it's the big guy, and here you are. And this, of course, is a 0, and you don't get 0 in the denominator. So the answer is that the big target will just sit there like nothing hit it. And I will show you that tomorrow. And you might be just a little bit pleased. What about if you have a massive projectile? This is perhaps even more interesting. Again, you take these equations, and because m1 is the big one, divide everything by m1. This then is named for 1, and here you have a 0. Here is a 1, and here is a 0. So the answer is that the final velocity of the projectile will be the same as the initial velocity of the projectile. But if you do this one, here's the interesting. If you divide by m1, because it's the big guy, you get a 2 up here, and a 1 in the denominator, this term going to 0. And so we get this result that if this hits this, this will go off at twice the velocity that that had. And that, I think, is not intuitive. This is a problem that you saw last year, and you will see again this year, that you're sending the projectile into the block, and then once the projectile has embedded itself in the block swings. This is known as a ballistic pendulum. And during this collision, momentum would be conserved. Because, at least horizontally, the momentum would be conserved because this is a collision, and all you have is internal forces, bullet pushing block and block pushing bullet. But energy would not be conserved, especially kinetic energy would not be conserved during that collision. Mechanical energy would not be conserved. Tremendous amount of heat generated. And then once the bullet is inside the block, it swings, and during the swing, momentum is not conserved. You have an external force. It's called gravity. After all, at the top, it stops in its swing. How can momentum be conserved? But mechanical energy is conserved during that swing. You have kinetic energy turning into gravitational potential, and I'm not going to go through the bother of setting up such a problem, but what you find is that typically almost all of the mechanical energy that was there in the bullet as it went in gets lost and turned into heat during the collision. Of course, this would change slightly from problem to problem depending on how massive the bullet is and how massive the block is, but it is a mind-boggling percentage of the energy that turns into heat during that collision. Finally, I want to take this kind of a collision in 2 dimensions or possibly 3 dimensions, although that's a little mind-boggling, that if it is an elastic collision, and we make the simplification. I think I failed to state earlier that the book states, back when they are introducing these 2 equations, that this, assuming that the target is stationary, if it were not, then you would just adopt an inertial reference frame where it was, and then you could use these 2 equations. Well, same goes here, that if this was not stationary, we could find a reference frame where it was. Otherwise, we'll have one more variable. But note that if the collision is elastic, then we will have momentum. Well, it doesn't have to be elastic. Because it is a collision, the momentum will be conserved, and it will be conserved component-wise. So this horizontal momentum at the beginning will be the same as the horizontal momentum of each of these 2 added together, and the momentum would be conserved component-wise. Vertically, no initial vertical momentum. You would have the vertical momentum here and the vertical momentum there, which I think you could see would have to be inverses, arithmetic inverses of one another. And because it is an elastic collision, we would have kinetic energy conserved. And so you would be working with these three equations simultaneously to try to do this problem. Note that there are, in fact, 1, 2, 3, 4, 5, 6, 7 unknowns. Then they are repeated, but to solve for 7 unknowns, you would have to have 7 simultaneous equations. You are not going to get any more equations than this. So for there to be a problem that you could do and get numeric answers, they would have to give you 4 of these unknowns. Then you could solve for the remaining 3 using these 3 simultaneous equations. Thank you.